시작할게요. 프레젠테이션 스케줄을 주말에 올렸고요. 다 확인해 보셨겠지만 한 번 더 확인을 통해 여기서 한 번 더 확인하죠. 11월 30일 다음 주 화요일부터 시작을 할 거고 개인 발표가 많아서 조가 좀 많다 보니까 날짜를 좀 많이 할애할 수밖에 없었고, 그리고 20분에서 15분으로 줄였어요. 20분으로는 도저히 소화가 안 될 것 같아갖고 한 조당 15분씩 발표를 준비해 주시고 3분에서 5분 아니면 1분에서 5분 정도 Q&A가 있을 거예요. 그리고 다음 주 발표조는 4, 6, 8조, 여기 4조 번은 여기 있고, 조 확인하고 네, 스케줄 이거 확인해서 이 6조가 다음 주에 발표를 하고, 그리고 8조 그 다음 주 마지막에 이 4조가 발표를 할 거예요. 네, 15분으로 바꿨습니다. 그 발표 준비할 때 유의해 주세요. 질문 있나요? 그리고 그 프레젠테이션 하고 그 기말고사 대신에 그 리포트 제출하는 것도 있으니까 신경 써서 해주시면 될 것 같습니다. Okay, so let's start the lecture. So in the last class, we have learned the PCA and sufficient dimension reduction. Okay. So we have learned two methods for doing sufficient dimension reduction. One is for the introductory idea, which use the first inverse moment, and the first inverse moment doesn't work when the response has U shape following the central subspace. So in that case, conditional expectation, the first moment will be just 0. So it doesn't have any information. And the way to extract the sufficient dimension reduction direction for this U-shaped data set, we can use the second moment. Okay, so you can see that the variation of the conditional expectation is moved over the direction that is orthogonal, is kind of orthogonal to the direction in the central subspace. So we are going to extract this part by using this direction. So this is the basic formula for the sufficient dimension reduction using the second inverse moments. And this part is to adjust the relation between in the geometric structure in the random vector x and the y. So we have this, and yeah, we conducted our simulations for this sufficient dimension reduction. And actually, the first idea, this third used moment events, is developed in 1991, and actually 1989, a little bit earlier than this paper published. The Kirchhoff provided an idea of this sliced inverse regression as a discussion regarding the generalized linear model. So the linear model, we start from here. So this is called a link function, and the motivation is start from when the link function is violated. Then what about the direction here? And this the papers prove that even though link function is not well specified, not well identified, the direction will be the same. So it's a kind of the groundwork for the sufficient dimension reduction. And same with the second moment And there's another method called directional regression, which is combination of this SIR and SAVE. So SAVE use the second inverse moments, but it doesn't work well when the true relation is linear. And the directional regression is address the issues that arose from the SIR and SAVE. And then in most of these cases, all of them use the inverse moments. And in most cases, it requires the assumption that predictors are elliptically distributed. So which means the density function or characteristic functions, their contour is, the shape is like this. The contour of the density function is elliptical. So normal random variable are one of these elliptical distribution, and many of the random variables follow this structure. And it's kind of intuitive that these methods, the inverse moments-based methods, they are like distribution free. So which means many methods use a particular likelihood functions to develop the method, but this sufficient dimension reduction doesn't use that. Instead, they use their moments. But as you can see from the structure of the variance, so variance is basically the variation of x, where variation of x minus the center, the directions, right? The variation of this from the center. So if the distributions are elliptical, the variance structure will provide meaningful information. However, if they are not elliptical, then like very skewed, something like this, then variation of x is not symmetric. So it's possible that the variance structure will not provide some meaningful information. So like something like this, some weird situation. So in that case, the variance will not provide meaningful information. So these sufficient dimension reduction methods based on inverse moments may not work. So, okay. And let's extend the dimension reductions we've learned to the nonlinear case. So when we learned the support to vector machines, I briefly introduced the kernel trick. So we can use this kernel trick to provide nonlinear dimension reduction. And it's very simple. So let's start from the PCA. So PCA is basically, we are looking for the directions. So direction, so if you make a restriction that the norm of the direction, the beta, the vector is 1, then this is basically the projection of x onto the space spanned by beta, right? So we want to find the direction that have the maximizing the variance of x. Right? So if x's are distributed like this, then this direction will maximize the variation of x. So it includes all the stochastic information regarding most of the stochastic information of x. So in that way, we can reduce the dimension from this to this PC1. And we ignore this PC2 part, as an error terms. We only consider these are our new variable. So we reduce the dimension from 2 to 1, considering the other parts as an error terms, not meaningful terms. Okay, so we want to maximize the direction like this, but it's basically the beta transpose x is mapping from the original dimension to one dimension, such that if we put x, then the output is beta transpose x. So in other words, this is equivalently stated as we want to find the linear map that maximizes the variance of x. So in this case, we have beta d, and here, instead of finding beta 1 to beta d, we just looking at the linear map from P dimension to D dimension. Okay, right. And the nonlinear PCA is just basically removing this condition. So this condition is just removed. Like we want to find the function of X that maximizes the variance. So, okay, so this structure is easily naturally extended from traditional to nonlinear, just removing the restriction, right? Because we just want to find the function of X that maximizes the variance. And we can do this by kernel trick. Okay, the kernel trick. So the reproducing kernel Hilbert space, we are going to develop the kernel for RKHS for the over p-dimensional space, say H. Then the member of the element in this reproducing kernel Hilbert space is a function from this original space to the real value. So in addition, if we have the kernel, the reproducing kernel for this reproducing kernel Hilbert space, then we have this property, the reproducing property is called reproducing property. So for any elements in this RKHS, and for any elements in this original space, the evaluation of F at X can be computed by just inner product between the element in RKHS and this reproducing kernel, where this inner product is using the structure of the RKHS. And in addition, for any element in this original space, this is like a basis for one of the bases for this RKHS, and the another basis, the inner product between these two bases can be computed very simply, the kernel of X and Y. In addition, if we choose the Gaussian RBF, the Gaussian RBF is our reproducing kernel, then this is then subset of L2 space over the p-dimensional space. And note that this L2 space includes the continuous function space, right? So any function that is continuous is also in this in the L2 space, and the RKHS generated by using this Gaussian RBF is a dense subset of L2 space, which means we can cover almost all functions that we can imagine using this RKHS with Gaussian RBF. Okay, so this is the most popularly used kernel. And then, so we have structure in an abstract way. Then how can you compute directly using your R or in your computer? So let's say we have the n observations in the original space, and then we apply this reproducing kernel like this. Then we can consider these are the n random copies of kappa of that X. So this is a random element in this Hilbert space. And these are observations, the random functions following this distribution. And now looking at the variance of, so now what we are going to do is we just do PCA over the RKHS using these new observations. So these are the random functions and observed random functions. So we are looking for just regular PCA. So regular PCA is we want to find the direction that maximizes this. And this is basically, we want to find the direction that maximize the variance between a variance of the inner product between beta and x, and the same. We are looking for the direction f in this function. So it's kind of functional direction that maximize the variance of inner product between the f and the random function. And by using the reproducing property, this is just we are looking for f that maximize the variance of f of x. Right. So if we use this structure, we can easily compute the optimization problem. Right. So, and again, so in our midterm example, some of you, did I provide the solution to that? So one of the problem is, if we set the optimization problem in the sample level space with reproducing kernel level space, then in most cases, the solution should be elements space elements in this space. So in the midterm, we have shown that the solution to the optimization problem at the sample level can be found here, although the optimization problem, we are looking for the function in the whole reproducing kernel hyperspace, but you can find the solution at this space. So it's kind of a justification of the results using the kernel trick by using the representative theorem. So anyway, so how can you compute this? So suppose that we have a sample space, we have the space spanned by a certain basis, and where the basis consists of this kappa of x1, kappa of xn. So these are the abstract space of the base, which is the space reproducing kernel level space with these are the bases. And let's make a matrix n by n matrix such that is the ijth element is just kappa of xi and xj. And these can be computed because the kernel is given. So like we can just put these values into your the Gaussian RBF kernel, for example. And this K is called the gram matrix in this H. Okay. And as we've seen in the midterm again, the coordinate representation of any elements here in n-dimensional. So H is n-dimensional because basis has an element. So the representation of element in H can be represented by a vector in n-dimensional space, such that for any app, it can be computed. We can find this vector such that this is just a linear combination of these bases, and where these are the coefficients for the basis. So after having this, and you can actually find this vector using this as well. Oh. The detailed computation is kappa of x. So we can evaluate this f of x1. So we have this. We can find this using this equation. So we can find this using the equation. In addition, the inner product between two elements in this RKHS is just this. So we can see that this is f I kappa dot xi, and g is summation of G and kappa dot xj. So J. So, and the inner product is the bilinear form. So it can be shown that this is just a simple computation. I, J, F, I, G, J, kappa of X, I, X, J. And if we have the matrix K, then we can easily show that the inner product is just F bracket transpose K and bracket G. Okay. Right. And furthermore, we can also compute the inner product between a function F and G operated with the linear map can be computed in this way, and where this matrix is defined in our midterm exam. And in the kernel PCA, this operator becomes the variance operator. So we can define the variance operator like variance operator such that we can find the variance operator from here. So let's say A is Hilbert space times Hilbert space to R such that F G goes to covariance between F of X and G of X. And this is a bilinear form. So we have the unique representation of this linear map, which is called the sigma, such that the inner product between F and sigma G is this. And this value is just I equals 1 to n covariance J equals 1 to n, the covariance between summation of F, F I kappa dot xi F J kappa dot xj. So you can actually compute this. I know. So this is just the expectation, the empirical distribution fx minus e and f of x, and multiply g of x minus e and g of x. And you can actually compute this sigma in the reproducing kernel Hilbert space by solving the equation. And after solving the equation, we can see that this variance of f of x is a form of just find the vector maximizing this. So it's like just an eigenvalue decomposition problem. So here, the optimization problem is over this just function space. And with this coordinate representation, we can show that this optimization problem becomes eigenvalue decomposition problem in n-dimensional space. So you can just put the eigen decomposition using R, then we have the coefficient vectors for this F. Okay. And after having coefficient vector, our first PC is a form of this coefficient and the vector, and look like that. So if these basis functions are nonlinear, then this is the linear combination of nonlinear functions of x. Okay. So our new predictor is like this. X and x. And we call the traditional PCA is we have the bare transpose x. Traditional PCA is from like this, but now like this. So this is just a check 1 to P, PRJ, XJ, something like that. And now this is a form of the kernel PCA. Any questions? All right. And the kernel saw can be easily extended, but I don't think you can follow this at this moment. So I just skipped the detailed derivation of the kernel saw. So this idea is almost the same. So y is just color. And now we have kernel and kernel.x. This is a random function, right? In a Hilbert space. So we are going to conduct such that we are going to conduct y and kernel.x are independent given that say phi1 that phi d, where these are phi1 and x, phi2 and x, phi d and x. So this is the same structure phi in the Hilbert space. So this is the same structure. Oh, sorry. So structure should be kappa.x, kappa.x, kappa.x. So these are the same structure as the linear sufficient dimension reduction. So we are looking for this phi that satisfy this, and this is exactly the same thing. We are doing linear sufficient dimension reduction to this space. So if this is y and this is the p, and we make a layer of the function space of function of this predictor space, and we are looking for the relation between this reproducing kernel Hilbert space and the response, and we are looking for this conditional expectation of x given y, something like that. So we'll see this will be our the estimation of sufficient dimension reduction. Okay, so this is the last slide of the dimension reduction, and let's move to next. So introductory deep learning. So deep learning is a very big area and very diverse area actually. And even nowadays, there are too many methods developed continuously. So we cannot cover this only using a few classes in this semester. So in this semester, so I have only a few times today and Thursday. So in these 2 days, I'm going to introduce what the deep learning is. It's basically neural network. And instead of the just applying the codes, we are going to look at how these codes works with the toy example. So we'll see this soon. And the recent deep learning methods can be easily found if you look at the Kaggle or the website. So I'll leave this work to yourself so you can easily apply the codes in the internet. But in the class, we'll look at a little bit more detail with the toy examples. And so it could be very introductory. And applying the deep learning methods, you can find easily in the internet. Okay. So slide 아니었구나. So let me upload these slides to the Blackboard. So there will be deep learning classes separately. So if you want to learn a little bit more detail, then you need to take that. Just like okay. So I just uploaded the slides. So in this slides, I will introduce the neural network and the massive computation backpropagation, which is just fancy name of using the chain rule that you learned in calculus. And CNN, which is the one of the deep learning architecture, particularly focusing on the image classification. Okay, so let's start from the neural network. So as you can see, it's about a network. So what the network? So this neural network is inspired by the way the human brain works. So we have input, the signals, then image is received through a human sense. For example, we have the signals input and processing through the neuron process signals if it exceeds a certain threshold to identify an image. So of course, this neural network, what we are going to learn this class, is different from the brain, but the idea came from this the work by the human brain. Right, so this is the basic structure of the neural network. So we have one hidden layer. So we have input, we have two inputs, for example, we have two features, or we have two predictors. Then we have two nodes in the layer. That in the first node, it is combination of the two inputs, say the W1, I1, and W2, I2. And the second node in the hidden layer is the linear combination of W3 and W4. And we assume that there's some bias, but in our terms, it's like an intercept, the common differences. So we call this B1. And in the layer, so this is, we have two. So this is the layer. And when the numbers came out from the layer, we have the output is output layer is like a prediction. We are going to use the number processed in this layer, and combining this, we provide class if this is a classification problem, and we're going to provide a number if we have the continuous responses. Right, so we will see this structure again and again. So next. So this is the case where we have two layers. So we have multiple inputs, and the hidden layers in the layers, it's okay to have multiple nodes that is not the same number of the input nodes. So we can freely choose the number of nodes, and we can also freely choose the number of the hidden layers. And the number of layers is called the depth of this deep neural network. But basically, the structure is like this. We have multiple inputs, and we may have the multiple hidden layers. And as we have more layers, then the results became more complex because we have the multiple weights, many different weights. So the interpretation of this deep neural network is very difficult. Okay. And there are many different types of networks. So this standard network is called just forward neural network. So input and output. And the recurrent network is this hidden layer is used again when we propagate the network. So the forward network is the propagate the data forward, and recurrent network is the data forward and also backwards as well. So this recurrent neural network is widely used in the speech recognition, voice recognition. So like when we have some sequence in the data set. So in speech or the document, it's a sequence of the words, right? So these sequences are not randomly observed. There's a specific sequence. Or stock prices also has a sequence. They are correlated if they are close to each other. It's not a different observation, right? So in that kind of data set, this recurrent network is widely used. And so basically the methods are just a network procedure. So in this class, we are looking for the way of computing the network, just for feed-forward network. So again, the basic mechanism is we have two inputs and the intercept part, and they call it bias in the machine learning community. And this is included the inside of this function f. So this is what the hidden layer do. And when the numbers out from these nodes, we have another function. It's called the activation function. So it's basically what this numbers is doing is this linear combination, where this is actually the affine transformation. We are looking for the affine transformation that extracts some characteristic in the data set. For example, if we are looking for the image, then we are going to extract this structure from the image, right? Then it can be done using just multiplication of this to this particular the partition of this matrix. So we extract some features through this linear combination, and this activation function is it may boost the signal, or it may reduce the signal, or do something. So we have the activation function and linear combination of the inputs. And when you have the multiple layers, then the output from this hidden layer will be another input from the next layer. So we can easily extend the number of layers, which will be the depth of the deep neural network. So in this case, we have only one layer, and the output is we are going to predict y based on this output here. And we can see the performance of this network prediction by just calculating the loss. So in this case, we just square the error loss, but you can apply different loss depending on the problems. Okay. And next is we may improve this network by modifying these numbers. These are called, altogether, these are called the parameters. And this function is usually given. So we can improve this prediction by modifying this. And this is just, we are going to minimize this, these loss functions. So you can see that this will be a function of the W1, W2, right? And we can minimize it by using the gradient of this loss function. So we talked about the gradient descent, I think, when we learned this. So when I talk about the boosting in the random forest, I talked about the gradient descent, right? The optimization problem. So tree-based method is also basically the solving the optimization problem. And gradient descent is we are moving the variables that follows the direction that lure the functions. So for example, in this very easy problem, when we have one variable, the gradient at here, this point, for example, is a slope, right? X, Y, delta X, delta Y. The variation of the function output over the distance, the variation of X. And this direction is basically we increase the function. So gradient is, the direction for the gradient is increasing the function. However, our problem is we want to minimize the loss function. So we just put the negative sign to the gradient so that it will decrease the function. Or in another way, if we put the negative sign onto this loss function, then we are going to maximize this negative loss. So anyway, it's the same. So we put the negative sign to this gradient. So same, maximize or minimize, it's the same. Right, so we are going to move this when you update this W, the weight. And here, then this might be a problem. How large gamma will be there? And this gamma is one of the tuning parameter in this deep learning neural network. So in optimization problem, we actually, the way of finding this gamma properly, like by using some other numbers, we can find the best gamma to find the solution. But in this deep neural network optimization problem, this is called the learning rate. So you can see deep learning community uses fancy framework, but the idea is very simple. So this is called the learning rate. If this rate is large, we move more. So the direction will be here. And if gamma is large and one step, we may go further like that. Or if gamma is really large, we may go like that. But if the function is not convex, if the function is like this, then the final solution may fall into the local minima that is not global minima. But anyway, so the learning rate is how far you want to make a differentiation. So if gamma is set properly, then it will go to the solution very quickly. But if it is too large, it may go to the solution that is not the global minima. Or if gamma is too small, then you may need more iterations. So it might be too slow to converge. So gamma is one of the tuning parameter. And we're going to update this W by using this formula. And we are doing this iteratively until it converges. And this is gradient descent idea. And there's also the variant or variation of the gradient descent method, which is called the stochastic gradient descent method. So it uses the randomness of the observations, or they call the batch. Divide the batch, and by using the Wick-Love large number, if we apply this Wick-Love large number, then eventually it will go to, the answer will go to the sample mean will go to the true mean. So using the idea of this, so they separate the partitioning the data set and compute these guys separately and taking the sample mean, for example. So there are some variation of the gradient descent, which is stochastic gradient descent, because they use some probabilistic model in the optimization problem. but I'm not going to make detail in this class. So which reduce the computational cost. So it's like a trade-off between the accuracy and computational efficiency. Okay, so activation function. So here the output from the layer is called the activation function. So basically it's like an abstractive process of neural network in each node. So, and these are some examples of the activation function. So inside of the activation function, the arguments of the activation function is kind of a feature, the kind of a local feature that you are looking for. And if the most simple activation function is the linear function. But we are not using this in this deep neural network because later we are going to extend the layers. And if this activation function is linear, then there is no reason to extend the layers. It will be the same as we have one layer, because we are going to use the gradient of the error functions, and this combination of the linear function will not improve anything. So we may need some nonlinearity in this activation function. And the simplest is the unit step, the step function. So activation function is like that. So this is not linear because it's not continuous, it's not linear. And so it provides signal that if axis, the inside, the linear transformation of axis is larger than 0, it will provide 1, and not, it will provide 0. So it's useful for binary classification. And sigmoid function is basically the logistic. And so when x goes to negative infinity, it will go to infinity, so it will go to 0. And when x is 0, it will be just 1, so 1/2. And it will go to infinity, 1 if x goes to infinity. So sigmoid function is like a logistic. Like this. So it's also used in classification. Like if this output is like close to 1, then we class this. We assign the class as the output with the largest sigmoid output, for example. And the softmax loss function is actually the activation function is basically just extension of this logistic. So here, when you have the binary classification problem, and softmax is when we have the multiple classes. And there's also another variation of the sigmoid, like a hyperbolic tangent, 1 to -1. These are also frequently used loss function. Activation function. And lastly, the loop function is most frequently used, in particular, the convolution neural network. So it's combination of the linear and the unit step function. So function is, it will be 0 until x equals 0. And it provides a signal that like this. So this activation function will not deliver any information when the affine transformation is less than 0, it's negative. And if the inside of it, the affine transformation, if this is greater than 0, it delivers the message as amount of the number in this argument. If it is large, then it provides large number. If it is small, it provides small number. So it's like a combination of between this linear and unit step function. And you can see this is also not linear. And the advantage of the ReLU function is is easy gradient. So you can see that the derivative of f, it will be 1 if x is greater than 0, and it will be 0. The gradient is actually this unit step function. So it is larger than 0, then it delivers the gradient. So when we do the back propagation, computation is relatively easy compared to the other, this nonlinear. Okay. Next, so this is again summarizing the forward and backward propagation. So forward propagation is basically prediction, right? We is processing from input to output. Just they used just fancy words. It's just prediction. Input to hidden layer, and this is output. We just computation. And if neural network with large number of hidden layers, we call this deep neural network. And back propagation is updating weights and biases. It's like looking for the parameters. It's like a kind of the estimation of the parameters. And through the iteration. So it's like the back propagation is estimation, kind of estimation. It's like a prediction. It's like an estimation of the parameter. So using the error or the loss function, we're updating W from this error at the final output. So the way of the propagating the network is in the backward. So it is called back propagation. Okay, so we update W to reduce this error as much as possible. Okay. So again, this is a general step. We have network. So if we have input, then the forward propagation provide the output. And when we update this, we first initialize the weights, W, or coefficients in our terminology. Coefficients and intercepts, initialize it by just random numbers or just fixed numbers, 0, like 1. And we feed the model first with these initial values and compute the output and calculate the error. So here it can be squared error or it can be cross entropy, depending on your problem. Then we update this W to reduce these errors, and we repeat this step multiple times until this error is minimized or this procedure doesn't change anymore. Okay. So there are some the pros and cons of applying this neural network. The first advantage is, of course, it's very flexible. And there's no specific rule for different rule for regressional classification. We can easily apply this method for regression or classification. What you're going to do is we just change the activation function or changing the final fully connected layer functions. And good to problem with large number of inputs. And once trained prediction is fast. So here, this procedure is like a back propagation from here to the W. This procedure will be trained using the training data. So it will provide the weights, W's. So after having this, with this iteration, fitting the new data set is super fast, just forward propagation. The procedure is fast as long as we have this W. So once trained, the prediction is fast. And this NN can be trained with any number of inputs and layers. So it's similar to the flexible methods. And it works better with more data points because basically, as we have the more layers, you will need more parameters. So the parameters, if you have too many parameters, it's likely that you overfit the data. So when you have a large number of inputs, then it will be good. And the disadvantage of this is we cannot interpret. So interpretation is the key problem. So if your problem requires proper interpretation, then it may not be a good idea. And the computational cost is also large because of the estimating the parameters by using the numerical method instead of the analytic solutions. So most of the computation is done numerically. So that requires a lot of computational costs. And of course, if you have too many layers, you may face the overfitting issues. Okay. So this is, I've already discussed. So forward propagation is starting with the initial value, just fit the data, and backward propagation is update the weights by finding the weights that reduce the errors. So forward propagation is again, so you have input and go into the hidden layer, and we have the hidden layer. So net H is we just linear combination of input, and output of this hidden layer is we apply the activation function after linear combination of this. And this will be a new input for next layer. But if the final output is the F, then Y. We have another this activation function to provide the output. Okay. And calculate the total error is, so here if you apply the square loss, this is an example of the errors. And next, back propagation is just we are doing this in the other direction by applying the chain rule. So for this particular example, this errors is a function of W through this relation. So first, so here this is procedure, we are looking for the direction of W that reduce or that increase this error. So here, WI is through the output of the network, output of this, and we have another out here. So this error is through this out, and this out is through the output from the network, and this network output is combination of these W's. So we can find the direction through this procedure. So it's just applying the chain rule. And this chain rule is computed from in the backward direction. That's the reason why I call this back propagation. After computing this, we can update W by using this formula where gamma is given as a learning rate. Okay, so forward and back propagations are repeated until it converges. And this is a little bit more detailed step. Okay, so this is the same structure we have. We have two inputs and we have two outputs. And if we have one layer, one hidden layer, then there are many parameters like W1, W2, W3, W4 for the first hidden layer, and next weights for the output from the hidden layers. And in addition, we have also the biases. And let's do the toy example with given weights. So for example, we have this is the structure. This is just given as an initialization, for example. And we are going to update W and W2 that minimize the errors. Okay. So this is just a tedious computation. but I just show that in the package you do, package you will run. So there's a procedure of computing this in the forward propagation. And in backward propagation, we have to compute these partial derivatives of the errors. And then computation is like this. So I'm not going to describe everything. This is just tedious computation, and it's very simple, but it takes some time to do this properly. So this is just computation. So as a toy example, let me show how it runs. I think I have code. So let me show a toy example for this backpropagation. So I think this is the same slide. Let's see. Okay. So let's see this with this toy example. So iteration, and let's, in this network, let's initialize the parameters. We have the 8 weights, and together say this is W. And the bias, we have 2 bias terms. Let me define as just B. And input and target values. So our inputs, and this is our output. And set the learning rate, you can change it later. And define the activation function. So in this example, in the network, I will use the sigmoid function for the activation function. Then the forward propagation is the W1, so linear combination of 2 inputs, and the H1 is combined with linear combination and the bias, and the second node linear combination bias. And you can see that these bias terms are the same for all the nodes in the network. And the output is, the activation function is, we apply this activation function for this H. And hidden layers to output layers. So hidden layers, we have the linear combination of the output from the hidden layers with a new bias, and apply the activation function. And the results is, we want to see just the output from hidden layers and the output from this, this is the output from after input the hidden layers and after the hidden layers. So these 2 outputs, right? Okay, so let's define this forward propagation function. And the error function is, so the result versus the out. The out is over here, our out. So we want to see just squared errors. Okay, so let's do this. The first, we just fit the model using the forward propagation. And these are the outputs, out 1, out 2, right? And so out 1, out 2. And then, so okay, result 3 is the out 1, and result 4 is the out 2. So we compute the errors, and this is about the back propagation part. So if you look at this back propagation part, the next page, you can see that the error terms is like this. The partial derivative terms is like this. So just taking the partial derivative, you can get this. Right. So I just put that into here, we can do this for the W's and the B1 and B2s. So this is the back propagation part. And after computing this partial derivative, I apply the same gamma, the same running rate, and we update it and show the iteration number, and we do this in this example 1,000 times. So let's do this. We store the error. We did okay. So let's see the errors. So we can see that the errors are reduced from like initially it was like a 0.3. And you can see that it decreases, and after like 200 iterations, the errors are very small, below the 0.004. So these are the results from this iteration. Okay, now let's do the prediction. So we updated W and B, and now our new prediction is like this: input and prediction. And let's see the output. It's pretty close to the, pretty close to this, right? So this is the two example for the back propagation. Okay, and next, let me show another example on the linear regression using here. So I don't know why. So in R, you can apply, you can install the Keras package with TensorFlow in R, but I don't know why with this Apple Silicon M1 chip, I cannot do that. I think I may need to change the versions, but I couldn't do that. So I just used the Colab. So Colab is the free project you can use from the Google. So you can Google Colab, C-O-L-A-B. So you can do this, the Python notebook over here, and you can use the GPU, and you can apply the TensorFlow Keras over here. So you can run the code from here. So in this example, you're fitting the coefficients of the linear regression using this new algorithm instead of the analytical solution. This is a way of estimating the coefficients using this algorithm we've learned here. So first, sorry, did I do this? I imported this TensorFlow package and NumPy package as the TF and NP, and this is to just draw the plot. So first, our original model we define is the y equals the 0.3x plus 0.5 plus noise. So this is our intercept. This is our coefficient. So x generated from the just random data set, and we add the noise from normal, and here is the example of x and example of y. So this is the data set we have. And now we are in the inference is we have the y and w times x plus b. So this is our fitted model. And initial value, we just find the w, the beta one, the coefficients from just a uniform random variable, and the intercept I set to be 0. So if you run that, so the initial value is 0.74, and 0 is the b, the intercepts, and y is the just fit the model using the same x data, and we assume that the x data is known, and y is the fitted value. And now let's define the forward function like this. Forward function is wx plus b. And in the optimization, we are using this optimization, the ADAM. This is the most popular used algorithm to optimize the function in the network. So let's define the learning rate as 0.5, and the loss function is just mean squared error in this TF keras. And the initial value is I just save this y. The y is, the initial value is the fitted value from this uniform random variable and the 0. So in this training procedure, we generally use the gradient descent method. So our prediction is the forward function and inputs, and loss function is using this mean squared error function. Put this is true value and this is fitted value. And gradient can be computed using this TF gradient tape. We put the loss function we define here, and this is the arguments for the loss functions. And we optimize this using the ADAM method, the ADAM optimizer. So plug in the gradient and the arguments. And this is the training procedure. So in this procedure, so I define, this is defining the function, and in the step in ranges from 0 to 200. So we have the procedure 201 iterations in this for loop, and we calculate the loss from this train step, and we update. The updated value will be stored over there. Okay, so we want this. So we have the 200 iterations. So here initial update is 1.24 and b is 0.5, and the loss was like this. And we apply this and we iterate this idea, we iterate this algorithm. Finally, the W now 0.3 and close to 0.5 like this. Okay, and this is the results, showing the result of the iteration. Okay. So the target values are two observations. So the y equals 0.3x plus 0.5 as we define the model. And we find these coefficients as considering these are the neural network procedure with the linear. Then we can see that initially it was like that. The W is from the uniform random variable and the intercept was 0. And after the iteration, the trained values is like this. So, and finally, W is the estimation of the slope. This is the estimation of the intercepts, and it's very close to the true value. So it's a kind of two example of applying the linear regression using the linear neural network. Okay, so let me stop here today. Next class, we'll see more examples of the network architecture like CNN or RNN, and I'll show you some demo example for that. And again, it's okay. And see you next week. See you on Thursday. And again, I should don't forget your project. So some of you should present the project by the next week. Okay. See you on Thursday.